Thanks again to the organizers for giving me this wonderful opportunity. It's been a pleasure being here. So following one's lead, I will try to give you an overview of the kind of problems that are being designed, or the kind of problems that are out there when you try to apply the kind of stuff that Juan talked about, which is ideas related to information or information theory. Try to apply them to messy biological systems. Okay, this sounds like a hopeless goal when you begin, because this notion of computation with biology, while it sounds very exciting and intriguing, it's a whole mess. It's like soft matter, and it's not clear what is, it's not clear what computes, it's not clear what counts, it's not clear what processes information, and so on and so forth. But over the last few years, people have made a lot of progress, and it has become clear that, or it is starting to become clear that you can actually come up with what looked like a cohesive set of design principles, a cohesive set of questions and frameworks to try and understand how biophysical systems measure information and process information. It's not, I don't have to emphasize to the audience, the necessity of information processing in biology. Cells constantly measure concentration gradients. Immune systems constantly, figure out what is a threat to the body and what is not. And all this requires computation or information processing on a very rapid scale. You have temperature gradients being measured, pH gradients being measured. And so fundamentally, one can ask two classes of questions. How does this measurement happen? What are the physical principles that let biophysical, that let cells measure concentration gradients, or that let cells measure temperatures? The second question we can ask is, how accurate is this measurement, and how can we make it more accurate? I'll mainly be talking about the second part. I won't be talking about the physical processes that are at, that are responsible for the measurement of temperature gradients and concentration gradients and so on and so forth. I'll mainly be talking about accuracy and how one can modulate the accuracy, or how one can control the accuracy, and how one can basically use the reasonably simple ideas from statistical mechanics to gain some insight into these control processes. Okay, so there is no way that I can actually do a good job of covering the entire field or covering the entire spectrum of questions that are out there. So I'll try to give you an overview of some of the most important concepts that I think are relevant to these questions. Again, as one did, it will be somewhat personal. It's going to be my personal take on this field. The first lecture is going to be mainly on the chalkboard. The second lecture will be PowerPoints. I'll sort of show you some illustrations of how one can use these ideas. And the third lecture will be a mixture of these two things. Stop me if you have questions. I tend to talk somewhat fast, as you would have noticed already. And if I'm not speaking clearly, let me know, and I'll be happy to answer questions. Okay. So the first question that we can try to sort of get our hands around is, let's think about concentration measurements by cells. Okay, so let's say we have a cell, and this is my cell, and this is my physicist's interpretation of a cell, and it has some sensors sticking out. Okay, and molecules can come and bind to the sensor and unbind from the sensor, and somehow the cell has to take these binding and unbinding, or these ligand binding and unbinding events, and transform that into information. Okay, so without going into the details of how the cell transfers it, let's try to sort of get a very back-of-the-envelope calculation for what the accuracy of information transfer is going to be in such a process. Okay, so typically, if I have a cell, and it has some protein sticking out of its surface, and let's say that the protein can bind to ligands inside a region with the radius a. Okay, so this a sort of represents my length scale. That tells me something about the size of the sensor region. That's about it. Okay, and if you have if the concentration of the species that we're interested in in sensing is C, then the average number of molecules that are going to be floating around inside the sensor region is going to be proportional to, and I'm going to be very hand-wavy over here, is going to be proportional to C times A cubed. This is the number of ligands that are floating around inside the sensor region, and adopting a very, very simple hand-wavy idea for error, the typical noise that we expect from measurements of this sort is going to scale like the square root of this average. So the larger the number of the larger the average number, the lesser the relative noise, or in other words, the typical noise scales like the square root of the number of measurements, or the number of molecules that are out here. So this is very hand-wavy stuff. It's very simple stuff. Nothing. I'm not introducing any new physical principles. Now let's say if I take a cell of the sort, let's say that it typically integrates concentrations over some amount of time, and I'm using these words as if this is a conscious entity. Again, I'm not going into the physical principles that allow the cell to do this, but let's say that the cell can sort of can observe concentrations over here for a certain amount of time tau, okay? And it can make a measurement over this amount of time tau. The number of independent measurements the cell can make, so this is the number of independent measurements the cell can make, is going to be given by this time tau divided by some notion of a decorrelation time. Okay, and how does this come in? If I have a set of molecules in here, I need a new flux of molecules to come in, push the old set of molecules out. I need the system to constantly get refreshed, and this decorrelation time can come in or can be related to the diffusion time scale or the diffusion constant that governs transport processes for molecules in the system. Okay, so given a diffusion constant, the time for diffusing out of this region, again, these are very rough back of the just the scaling limits. The rough time scale taken for this envelope to be refreshed constantly. The rough time scale for that is going to scale like this, the radius squared divided by d, where d is the diffusion constant for the system for this medium. Yep. Different types of what? Yeah, so right now I'm not considering all those things. I'm just saying let's just say we have one ligand and I want to sense the concentration, okay? And I'm trying to come up with this very back of the envelope calculation. And what I'm interested in is an estimate for the error that the system is going to have as it senses concentrations. Okay, and that's what I'm trying to get at with all these things. I already have a typical noise measurement, and now I have. I'm going to try to come up with an estimate for the number of measurements that the cell can make, and I'm going to use these two to come up with an estimate for a variance. Right? You had a question?
This cavity is assuming that the receptor is
Yeah, diffusion is the main thing basically, right? So that's the kind of limit I'm in. So the number of measurements that you have here, the number of independent measurements is tau over tau d, and this is equal to tau d by a squared. And so I can put all this together, and I can say that the typical, if I want an estimate for the typical error that the cell makes as it measures concentration. So delta C is my error. It's going to be a square root of a variance, and C is the mean concentration. This is going to roughly scale like 1 over the square root of n divided by n measurements, and so this is roughly 1 over square root of d a c bar tau. And this is just a scaling calculation. This is very ad hoc, right? Such a limit was first derived by Berg and Purcell in a landmark paper from the 1970s. This is the Purcell here is the same Purcell associated with NMR, and so they considered this biophysical question for various reasons, and they came up with this very simple idea, or with very simple limit for the error that a cell has to make as it measures concentrations if it uses these very basic transfer properties. The thing that I want to point out here, which is very interesting, is that there are no kinetic parameters anywhere in this limit. I haven't thought very carefully about the binding rates and the unbinding rates. A lot of the details or the morphology of this process is suppressed. Everything is captured in terms of an effective size, a diffusion constant, and that's about it. Yep. This is delta C. So delta C is the error the cell makes, or it's basically the square root of the variance of the concentration fluctuations. And if you use these principles, this very ad hoc principles, you get this bound that doesn't depend on any kinetic parameters at all. It depends only on the. So the tau d thing signifies the amount of time the ligands take to diffuse out of this volume. Okay, and that sort of gives me a measure of decorrelation time. Because if I have the same ligands binding to the region, I can't, my errors are correlated. And in some sense, if I want my processes to be decorrelated, I want a new batch of ligands in here and the old batch to be diffusing out. And that's what this tau d sort of gives you. Okay, so again, this is. One can do a really good job of writing down actual kinetic equations and so on and so forth, but I have not done that. I'm very lazy right now, so I just did this very simple thing. Okay, the reason I started off with this is to sort of point out that in this ad hoc principle or this ad hoc set of calculations, you seem to get this limit that doesn't depend on any kinetic constants. And what I'll be spending most of my time today is working with quantities of this sort. What is the error that's typically incurred if as cells make measurements and so on and so forth. And what I'll try to tell you, or what I'll try to sort of argue, is that this limit is actually set by fundamental statistical mechanical equations like the laws, like the fluctuation dissipation relation, and that will then help me, it'll help generalize these ideas, and then we can ask questions about how we can actually improve these bounds. So that's going to be the structure of the first of my talk today, and in tomorrow's lectures, we'll talk a bit more about using non-equilibrium forces to strengthen or to reduce errors and so on and so forth. Okay. Any questions about this? All right. So a lot of what I'm going to talk about is actually based on William Bialek's Biophysics textbook, and I'll put a link to this and a link to a few papers, and I'll send it to Anupam after the talk. I've already provided one of the references. One of the references in my abstract already has most of this thing. So this I find is a very useful book. It has concepts of information theory. It has concepts of and it marries them very elegantly with concepts of biophysics. And that's what I'm going to be basing most today's talk on. Okay, so let's take a closer look at this. This is very ad hoc, but what I'm going to try to argue is that this ad hoc principle actually reflects reflects fundamental constraints imposed by the linear response theory and the fluctuation dissipation relation. So I'm going to sort of take these ideas now, write more detailed models, and see what we get. Okay. So let me go back to my toy model. I have this receptor. I have ligands binding and binding from the receptor. And let's say I have a rate for I have a certain rate for binding, and that's K plus. I have a certain rate for unbinding, that's K minus, and let's say I have a certain concentration of ligands that are floating around in solution, and so this concentration is something that I want to measure. What the system has access to are binding unbinding events. So I have typically some amount of binding, I have some amount of unbinding, and what I can write down if I define. And there's going to be some math as I start off, but hopefully these are simple equations, and you can ask me questions, and hopefully they'll become clear as we go on. So what I'm going to define now is n of t, which is basically a probability or a fractional occupancy of this the receptor, and I can write down very, very simple mass balance like equations or master equations for how this fractional occupancy of this ligand changes as a function of time. Okay, so if I want to write down an equation of motion for this fractional occupancy, this is a balance like equation. So there's nothing, we can just sort of think about all the processes that can happen. The system can lose ligands at a rate k minus. Okay, and so that's a loss term. The system can gain ligands at a rate k plus times c, and the term multiplying this k plus times c, which is 1 minus n of t, is simply a probability associated with with this receptor being unbound in the first place. Okay, so this is very simple. It's just writing down mass balance like equations, and this is my constitutive equation for how the number of ligands bound to the system changes as a function of time if you give me k plus k minus in C. Okay, and what I want to be able to do now is I want to be able to compute something that looks like I want to be able to sort of compute. I want to use this series n, this time series n that I can get if I were to stare at this ligand and if I were to sort of see what happens to it. This n would have a time series that looks like this. It would be bound at some points and unbound, and so on and so forth. And what I want to do is I want to take this equation and try to come up with a bound on the variance of n of t, which will then help me get a variance for the concentration, and we'll see if ideas of this sort are actually relevant, or if this ad hoc principle has any basis if you start from a fundamental equation of motion. Okay, so if you before going ahead, let me just define one more quantity. And again, this is just a lot of definitions. The mathematics is really simple over here. The ratio of binding to unbinding, the total binding rate to the total unbinding rate, I'm going to define as the exponential of some binding free energy. F is a free energy, or it's a free energy force that sort of tells you how likely it is for the ligand to be bound to the system or unbound to the system. Okay, so this F controls the rates of binding and unbinding, and I'm going to define this. I'm going to define this quantity. N is oops. Okay, sorry. Let me just redefine this a bit. It's a mistake. N, I've defined n as a fractional occupation, so n can have any number from 0 to 1. Let me read out this as occupancy of. So the occupancy of this receptor can either be 0 or 1, and n in some sense is the average of this occupancy. Okay, so that's sort of what we are going for. All right. Okay, so what I'm going to. Sorry, what? Over here. So it is a convention that I'm using. I could redefine everything so that the rate of binding is only k plus, but I want to explicitly have the concentration in here because I think of it as a chemical potential of some sort, right? And so typically when you have binding and unbinding events, there are two things you can control. If you're in a dilute limit and you have no control over the concentration, then you'll only have k plus. So everything's determined by how strongly the ligand interacts with the binding surface, right? And all that is in k plus. But if I can control the concentration, or if I can control the chemical potential of the ligand, that also is going to influence how I bind and unbind, right? And so that's why I have both of these. Sitting up here. So in some sense, this is a generalized rate for adding something on, and you can control two things independently. By controlling the surface of the ligand, you can affect k plus, and by controlling the concentration of the ligand, you can sort of change C. And so both ways, you have two routes to controlling the total binding rate, and that's what's going on over here, right? And k minus, again, it's a convention. I could have chosen this so that k minus was some part of the concentration also showed up in the K minus. Right? So right now my convention is that addition events are determined by the concentration. Removal events are independent of the concentration. That can be different. It's just a convention I've chosen for now. Everything that I talk about, it turns out to be independent of the convention. Okay. All right. So this is what we have. This is a nonlinear equation. If I think of C and N together for how the average fractional occupancy of this ligand changes as a function of K plus C and K minus. Okay. So what I want to do is I want to be able to commit something like this. Get at an estimate for an error. And so what I'm going to do is I'm going to linearize this equation. I'm going to assume that there are small fluctuations in that the value of n fluctuates about its average by a very small amount. Also, I want to sort of point out that the concentration that shows up over here, the concentration of ligand species over here, and K plus and K minus, all these rates are subject to thermal fluctuations, so they fluctuate by small amounts. And what I'm going to do is I'm going to incorporate all those fluctuations and expand this equation in linear order. It's a simple algebraic step. I'll just write down the answer without justifying all the steps that go in between. But if I were to do that, I get this somewhat messy equation which I'll reproduce for now. Yep. Yes, exactly. So K plus and K minus can be modulated by controlling how the ligand binds. If I charge the ligand by some amount, it'll change K plus and K minus.
And the free energy of what?
So I'm defining this entire ratio as a free energy,
okay.
As an exponential of free energy. And I'm defining it that way. And where I'm heading with all this is that I'm going to allow these quantities to fluctuate, and so effectively I'm going to allow this free energy to fluctuate. And that's where I'm heading with this. And if you do that, if you end up looking at a linearized equation, and this is a bit of a mess, I'm going to write it down, but hope after this we don't have to go through all these steps again. So what I've done here is I've said, well, n can fluctuate about its average concentration, and that's so I've said that n is equal to n bar, which is an average plus a delta m, and I'm only going to worry about the way n bar changes. And I've also sort of used the fact that for a system that's soft and that's messy, this entire free energy, or in other words, these K pluses and K minuses also fluctuate about some average quantities. And if you go ahead and do this, there are a couple of steps that I've skipped that are there in this set of papers in this book. So I'm not going to repeat them. You end up getting this equation. The only point I want to make here is that this equation is linear in these delta n's. Okay? And this force that shows up over here looks a lot like a fluctuating force. Okay, and for experts in the audience, you would have seen equations of this sort in other contexts before. This looks a lot like the kind of equation that you would get if you consider a system in a harmonic potential under overdamped conditions. Okay, so let me imagine a system that's in a harmonic potential with overdamped conditions. The kind of equation you'll get. So if I have a particle in a potential, it's a one-dimensional potential, and if I write down the equation of motion for the x coordinate of the particle, I get in the overdamped limit, you get equations of motion that look like this. This is a fluctuating, or it's a white noise term, or it's a random noise term. So this is the kind of force that you get if you consider the fluctuation, if you consider fluctuations of an overdamped particle in a harmonic spring. And the reason I went through these few steps is just to point out that if you were to write down a biophysical model for ligand binding and binding, you end up getting a structure, in the appropriate limits, that looks a lot like the structure you get when you think about particle, when you think about a single particle fluctuating in a harmonic potential, in some sense, this entire thing is a combination of a restoring force and a friction. This quantity, in some sense, represents what looks like a friction, and this quantity sort of looks like a fluctuating force, and it has a very similar structure. The reason I want to make this analogy is that for systems like this, we know a lot about how to think about fluctuations in these systems. We know what happens to these systems if I add external forces. We know that systems of this sort satisfy so-called fluctuation dissipation relations. In particular, what do I mean? So let's say I take the system and I apply a time-dependent force to this system, okay, on top of this random force. What happens if I want to predict the response of my one-dimensional particle to an external force that I apply on top of this potential, I can do so using linear response theory. I know that I can express x of t as in this simple form. I know that I can express the response of the system in terms of some function alpha that depends on the properties of the system in the unperturbed state times the force, the time-dependent force that I'm actually applying on the system. So here I'm sorry for the bad notation, F here is my new time-dependent force that I'm applying, and X is my is the response that I actually get. If I do the whole thing in Fourier space, this becomes more familiar. So if I take Fourier transform, this convolution integral becomes a product, and people refer to this quantity as a generalized mobility. This is my generalized, the Fourier transform of my force. So this is something that we know from linear response theory. We know that this is the exact for systems of this sort, and we also know that this quantity is something that can be estimated entirely in equilibrium without any fluctuations, and we can use this quantity to predict what happens to the system in the presence of driving forces which are time dependent. Okay, so just to complete my definitions here, alpha of t this is just a Fourier transform of my of this quantity. I also know from fluctuation dissipation theorems that this mobility is nothing is related to the fluctuations of the system in equilibrium. In other words, I know this relation. So this is just another fancy way of writing down the fluctuation dissipation relation. The mobility of the system, which is this quantity that determines how it responds to external forces, is governed entirely by this quantity S as a function of omega, and S is S of omega with the subscript x is nothing but the Fourier transform of the so-called structure factor for the system. Okay, so if I were to construct the time correlation function of the system in equilibrium in the absence of any forces, so capital F is equal to 0. If I were to construct this correlation function, I can take its Fourier transform and I get this object which I refer to as S of omega, and this S controls the mobility of the system, and I can use this object to predict to predict how the system will respond to fluctuations. Okay, the reason I'm sort of all these are just statements of the fluctuation dissipation relation. So this is still equilibrium. I'm not talking about any fancy non-equilibrium things yet. I'm just using elements of equilibrium statistical mechanics. And the reason, again, the reason for me to introduce these ideas again is that by analogy, this if I had a theory for this quantity, x of t, for this time correlation, x of t plus tau, which is completely captured by this Fourier transformed object. If I had a theory for this quantity, that's basically what I'm looking for, because this is effectively a variance of fluctuations. And so if I had a theory for this, I can go ahead and predict quantities of this sort. Okay, and so by using this analogy between the structure here and the structure of that shows up if you think about particles and particles moving around in springs, what one can do is one can postulate. Let me write this down here. I'm skipping a few steps here and there, but hopefully the essential message is clear, or I'll be happy to answer questions, obviously. So even for this system, even for this biochemical system, I can think of defining something that's my mobility. Now I'm doing this for the biochemical system. For the biochemical system, this mobility is going to look like the ratio of delta n to delta f of omega. So this, it's going to, over here, my mobility was the ratio of the response of the system to the driving forces. If I think of this as the driving forces plus a fluctuating force, which is what I was trying to do, then the mobility of this set of equations is given by the ratio of the Fourier transform of the fluctuations in n and the Fourier transform of fluctuations in the force. And I can take this equation, I can again go to Fourier space, and I can solve it, and this works out to this very simple result: k plus c Okay, so again, I've just taken if you just take a Fourier transform of this result of this equation, you can construct, or you can work out what the mobility is going to look like, and that's what we get. And again, from the flux, if this, assuming that this entire detection process happens in equilibrium, what I can then do is I can postulate that the imaginary part of this mobility, which I have constructed by going to this by sort of doing these linear response like tricks. This imaginary part of the mobility is proportional to the structure factor for n for the number of fluctuations. Okay, and the limit of omega going to 0 of S and omega is nothing but delta n squared. If I go to the limit of very low frequencies, and if I were to look at the Fourier transform of this object at very low frequencies, I get nothing but the zero frequency limit, and that's exactly the variance of the number of fluctuations, and that's what I'm looking for. And so all this ends up, this framework that I have sort of hand-waved my way through helps us, or lets us get an estimate for what this delta n squared should be. And this is just for completeness. This ends up looking like if I take the limit omega going to 0 of the imaginary part of alpha of omega, you end up getting finally n bar times 1 minus n bar. And so if you go through all these calculations, you end up getting an exceedingly simple result. You get the result that the variance of number of fluctuations that the system senses is nothing but the product of n, the average occupancy, times 1 minus n. And these kind of structures are characteristic of Poisson processes in the first place. And so it's not we end up getting something that we sort of expect. This result doesn't depend on k plus and k minus, and doesn't depend on the geometries of the system. It doesn't depend on any specifics. So the reason for doing all this again was to show that if we appeal to the fluctuation dissipation relation for these binding processes, we seem to get estimates for these variances or for these errors that start to make that actually make physical sense. Okay, so this is now in this case I've ignored diffusion. I've not put in the fact that the system that molecules can diffuse in and out. This is a very simple model for particle binding and binding. But I just wanted to sort of use this model to illustrate the fact that the fluctuation dissipation relation, which we know and love for, and it's the cornerstone of modern spectroscopy in chemical physics, actually also controls the kind of errors that propagate through biology. Okay, so the only control or the temperature scale here again controls errors. This is exactly the kind of things you would do, or these are exactly the kind of calculations you would do if you are trying to build a chemical spectroscope. And the point I'm trying to make, even if you ignore all this algebra, is that if you come to a biological system, you have to think exactly the same way. The ideas that help us build better spectroscopes can also be applied to biology and to get estimates for errors and to think about how cells can count and not count. Okay, so the fluctuation dissipation relation fundamentally sets bounds on how accurate measurements can be. In this case, I've ignored diffusion. I'm going to put that in. But you had a question before that?
Do you still need omega in the denominator?
Yeah, I mean, so this is it might. I don't think it's a typo, but I'll check it out. But no, it works out. So if
When you're doing the limit of S equals to
oh, I'm sorry. Yeah. Sorry. Thanks. Yeah. So if you end up working it out, the omegas cancel in the right places, and you end up getting this thing.
This means the fluctuations vanish in the kind of zero or saturated.
Exactly. So again, I mean, this is so in the zero limit, it's easy to see why it vanishes, right? I mean, there's nothing there in the first place, and so it vanishes. So I mean, it's in a sense, it's sort of like the. Okay, so in one limit you have Poissonian statistics. In the zero limit, this looks like the error or the fluctuations or the variance of fluctuations scales with the mean. Okay, and that's sort of a characteristic of Poisson statistics, and that makes sense. There are no correlations. You have things coming on, coming off. They don't really care, and that's what happens in that limit. And in the saturated limit. Again, you have a large occupancy, and so in the limit that the system is almost always occupied, or the limit that you have very high free energy, again it sort of makes intuitive sense that you kill this. But at least in the low density limit, this is just the Poisson. This is just an equation that reflects Poisson statistics again, and that's something that we have put in and we should expect. Okay, does it make sense? Okay. Any other questions about this? All right. Let me take this out. Okay, so what happens if I now put diffusion in all this? Again, it's somewhat of a mess, but let's write down the equations. I'm not going to go through everything again, even in this detail. If you go to Fourier space, it's very easy to do. It just looks algebraically messy. So now let me rewrite my basic mass balance equations. And now I want to imagine that I only care about concentration at a particular point in space, because my ligands my receptors are finite regions, so they only care about concentrations in a particular point in space. I'm going to denote that point by x, and I get an equation of motion that looks like this. And I now have to also think about how the concentration varies as a function of time, and this is going to be my diffusion fixed law. This is my diffusion equation. So this is one part of the balance. The second part of the balance comes from here because if my ligand gets adsorbed at the surface, I have to account for that over here. I have to put a negative term, and I'm going to put that. I get okay, and so this sort of comes because of binding from receptors. So even in this case, even though we now have a coupled set of equations with mass fluxes and everything, what we can do is we can go through exactly the same kind of steps as we did before, and we can basically write out an expression for Sn as a function of omega. Again, I'm not going to go through this right now. I'll leave it as an exercise, and it's useful to just you can just follow the kind of steps I have there, linearize these equations, and go to Fourier space. You can work this out. It's a useful exercise to do once. And what you end up getting, and I'll just write down the final result, is the following. You end up getting n bar times minus n bar pi AC plus 2 pi minus. So I'm basically following the fluctuation dissipation theorem and applying it to these set of equations. You can work out a formula for I'm sorry, this is the limit of omega going to 0 of S and omega, because this is the limit that we're interested in. This is the high time limit. This is the long time limit, because in this time limit, this entire object ends up becoming delta n squared, and this is what we're interested in. And so this delta n squared ends up looking like this quantity plus this other quantity. This has all these constants. The basic point I want to make from this is that this second part is always positive. It's never negative. N is always less than 1. And so from all these considerations, or just using the fluctuation dissipation kind of ideas, what you end up getting is that delta n squared, or the error or the variance of n fluctuations, is always greater than n bar minus 1 minus n bar whole squared divided by the square root of pi d AC. Okay, this is remarkably similar to what we worked out before over here. This was just an ad hoc bound that we worked out. There are still a couple of steps to go from delta n squared to delta C over C. Again, this is something that I'll leave for an exercise. But as you can see, the basic message that I wanted to convey here is that if you were to write down detailed equations of motions for how cells sense information or sense signals, ideas like fluctuation dissipation that we know from that we always use in other contexts actually impose fundamental bounds on how effectively or efficiently the system can capture information. Okay. Sorry, what? Yeah, so I'm sorry. So I just wanted to say this is greater than this number. I just wanted to put a bound on it. Okay, so this is always positive, and so the idea here is that no matter what you do, no matter how you change your, no matter how you design your kinetic parameters, you can let's say you have very high binding rates, or let's say you modulate these k pluses and k minuses so that they're very efficient. Even so, you cannot violate this bound, at least as long as the fluctuation dissipation theorem is satisfied, or as long as the Brownian motion is satisfied, or the laws of statistical mechanics are satisfied, and the diffusion, the size of your system, and the mean concentration of your surroundings in some sense conspire to put a fundamental bound on the messiness of on errors in information processing. So I'll leave it as an exercise to go from here to here. It's just a few more lines of algebra. Yep. Sorry, what? Yes, so n bar in this case does depend on k plus and k minus, but it's a combination of k plus and k minus. And in some sense, yeah, those factors always show up, right? No, yeah, no. I mean, the fluctuations in n do depend on n bar. If you actually end up taking this and transforming into fluctuations in C, you'll find that a lot of this actually drop out, and you'll end up getting a number that's only this thing. Okay, so up to this point, yes, it does depend on k plus and k minus, but n is a reporter of C, and so if you deconvolute that noise out and you go back to this, you'll end up getting this. You'll end up getting basically the same thing. I think the factor of pi is extra that sort of shows up from this more detailed calculation. Everything else is the same. Okay. As you can see, there's no tau over here right now, but that's sort of, I have to again sort of argue that there's a measurement time and so on and so forth, and then go from n to C, and that's where these n bars go away. Okay. Anything else? This is, yeah, C or C bar. It's all the same right now. Yeah. So again, I mean, these things are there in the reference that I pointed out before. But I just wanted to sort of, it's a very useful set of ideas to work through, because they show you how we can apply StatMech, concepts from StatMech to these biophysical problems, and the numbers that you get from these are very loose bounds. So, for instance, if you were to apply these kinds of bounds to the E. coli motor, and if you were to plug in values of the diffusion and the concentrations and so on and so forth, you get a number that tells you that the E. coli motor operates at an efficiency that's greater than 4%. So it's a very loose bound. It's not a very tight bound. One still needs to do a lot more work, but nonetheless, it gives you an idea for how information transmitted through biophysical channels is fundamentally affected by thermal concentrations. And this is also a very good segue into the next set of questions, which is, okay, so now that I have this, and now that I know that this kind of a bound is imposed by the fluctuation dissipation relation, how can I do something to actually violate it? Can I do better? Can I go to systems that are out of equilibrium, and can I reduce the errors? What happens if I introduce correlations between receptors? These are many questions that people are working on right now. I won't go into all of them. Obviously, the question that I'll be concerned with for most of the remaining part of this lecture and for the most of the next two lectures is what happens if we start violating the fluctuation dissipation relation? What happens if we go out of equilibrium? Can we actually end up doing better than this bound, and can we enhance the efficiency of information transfer? Okay, so in order to move ahead, there will be some amount of repetition. I'll actually introduce the concepts that were introduced in the first lecture again, because these are useful. So I have up to now talked about errors or fluctuations in concentrations. The next question that one can ask is, let's say I give you a pulse of concentrations, how much information is actually stored in that pulse? How can I quantify that? And for that, I have to use concepts like Shannon entropy and so on and so forth. And just for completeness, I'll just sort of write down those ideas again, and I'll introduce very briefly, because most of this was done today morning. I'll very briefly talk about Shannon entropy and mutual information and so on and so forth. And the point of this, the second thing is I'm trying to go from this picture where we have the fluctuation dissipation relation and these bounds. I'm trying to ask what happens if you start violating these bounds. What happens if you go out of equilibrium? Concepts like, in order to sort of start answering these questions in a quantitative manner, I need to think more carefully about information. And as was introduced today morning, one of the central concepts that actually is very useful in this exercise is the notion of Shannon entropy or Shannon information. And so this is going to be somewhat repetitive, but hopefully not too much. So as we discussed today morning, I mean, if you have a series of probabilistic outcomes, the Shannon information gives you a bound for how much the Shannon entropy gives you a bound for how much information is contained in those outcomes. We can put a factor of KB here if we want to think about thermal things, and if you don't want to think about thermal things, this factor of KB need not be here. Someone asked a question about this and one referred to this. So this object or this quantity, the Shannon information, is or when Shannon derived it first, he had in mind a game that had nothing to do with thermodynamics, that had nothing to do with physical measurements, and so his game was about questions, and the question he was trying to, or the problem he was trying to solve was how much information is contained in, or how do you quantify the information that's contained in a language or in a series of questions. And he wanted to write down, he wanted to come up with a quantity that's consistent with three basic principles. The first is, let's say you ask, you have a physical observation for which there are n equally likely outcomes. Okay. Then the information content or any attempt that you make at quantifying information content should scale with the number of outcomes that you have if everything is equally likely. So that's one of the structures that he had in mind when he thought about Shannon when he construct this thing. The second principle that he wanted this information content to satisfy was, let's say you split up your question into two sub questions that are independent of each other. The information that you gain should be additive from the two sub questions. And the last thing, which is an extension of the previous statement, was if you have a question that has many different parts, then each time you gain information, you want a quantity that in a series sort of reflects the amount of information you've gained as you go through a multi-part question. So this is basically what one discussed today morning, and it turns out that this. And it's a very interesting exercise to actually go through. It's a simple exercise, but it's a cool exercise to go through. It's a few lines of proof, and you can prove that this object is the only object that actually satisfies these three constraints or these three conditions. And that's how Shannon worked it out. There was no notion of thermodynamics. There's no notion of energies and so on and so forth. It was purely based on logic and inference. But it turned, this quantity has, as one pointed out today, and as we'll see in the, tomorrow and day after, this quantity actually shows up in thermodynamic contexts. It shows up in statistical mechanics for sure, but it also shows up in many of these biophysical contexts. And there is a way to go between this object, which has nothing energetic built into it, and ideas like work and entropy, which are fundamentally, or work and heat, which are fundamentally based on energies. Okay. Okay. So now that I have this object defined, let me now use these. Let me now take these ideas and sort of construct this very simple question. So let's say I have. Let's say I have some sensor for a biophysical system, and because of noise from thermal fluctuations, the input to the sensor, that's this variable x, gets gets modified into a variable y. Okay, and this quantity here is a noise due to fluctuations. Okay, and so in the context of what we discussed in the first hour of this lecture, this noise shows up just from thermal fluctuations. And so if I take a sensor, if I take a biochemical if I take a cell which is measuring concentrations, those concentration measurements are obviously always colored by noise due to thermal fluctuations, and you end up getting a result that is that depends on the actual signal you put in, and this G is just a multiplying factor. It's a signal processing factor plus noise due to all the fluctuations and that come from the fluctuation dissipation relation. And the question that again is a useful exercise to do is how is our uncertainty of this quantity x reduced if we actually end up measuring this object y, because I've put in some noise here. I'm obviously going to add some uncertainty to this to x, and we can try to ask how is this uncertainty changed. And so for this, I'll define this object, and this is I'm going to end up redoing some part of the mutual information stuff that one did. I'm going to define this object delta I of y comma x. And this is, I'm going to define this as S of x minus S P of x given y. And so this delta I, this variable that I've defined, it is a difference of the entropy of the signal x. So this is the inherent fluctuations in signal x. And the entropy of the probability distribution of x given you have made a measurement y. And so this was something that one introduced in the morning. In fact, it turns out that if I take an average of this object over all possible measurements of y, then this average is nothing but the mutual information between x and y. And this works out, let me just write it down again for completeness. So I've just gone through the derivation in some sense of the mutual information again. If you start off with the Shannon information, and then you construct this quantity delta I, which basically reflects the change in the information that you get by measuring y, because you take the entropy of x and you subtract from it the entropy of the distribution p as a p of x given y. And if you take the average of this quantity, you end up getting this mutual information. And this basically tells you, it tells you about correlations. It tells you about how measuring y reduces your uncertainty of x, and so on and so forth. Again, as one pointed out, this is always non-negative, and this has a form. That looks like a relative entropy or a Kuehl-Black-Leibler divergence. And it's again an interesting exercise to sort of go through, and it's just a couple of lines. You can show that this quantity is always non-negative. It can never be negative, and it becomes zero when x and y are uncorrelated. So if this noise becomes really high, such that it destroys, it overwhelms this deterministic part of this equation, then this object is going to become this p of x comma y is going to basically be equal to px py, and this entire thing goes to zero, and this mutual information goes to zero. But if this noise can be controlled, and this noise effectively reflects what we worked out over here, then we can efficiently transmit information through the kind of processes that we have. Okay. This object I has no upper bound. It depends on how strong. It depends on this object, this number G. And so by tuning G, you can sort of encode more and more information. But it has a lower bound, and the lower bound is basically 0. And one spend some time on this, but it's useful to sort of it's useful to just think a bit more about relative entropy before we move ahead. And this goes back to Steiner's lemma that one mentioned towards the end of his lecture. And let me just take a few seconds to work out what, or to give you a better intuition for what the relative entropy actually, does. So just to remind you, the relative entropy D between two distributions, P and Q, is sort of an information theoretic measure of distance, but it's not symmetric. And this is the integral of P log P over Q. And in order to get a sense for what this quantity actually means, let's say we have two distributions, P and Q, as we have over here, and let's say we sort of draw out n samples from these two distributions. Okay, so we draw out a large number of n samples from these two distributions, and let's just construct the probability of seeing the samples given or assuming that they were sampled from the distribution Q. This probability is going to be is given simply by a product of. So if I have these S samples and I have NS types of sample S, then the probability of observing these samples given I sampled from P is going to have this very simple multiplicative structure. I can write down a similar thing for probability of samples given Q. And just to complete the point today morning about Steiner's lemma, if you were to construct this likelihood or this probability or this ratio, P samples given P divided by P samples given P. So this ratio, in some sense, tells you, if I draw out n samples, what's the probability that they actually came from the what's the probability that they actually came from the distribution P as opposed to coming from the distribution Q? Okay, so that's what this ratio sort of tells you. These numbers give you the probability of finding the samples given that they were drawn from the distribution P or the distribution Q, and have constructed this ratio. And if you actually work this out, and this is again a very simple exercise, you can show that in the limit of very large n, this P works out to 1 plus 2 to the power of minus n d pq. And so this likelihood or this probability function basically goes to 1 as n goes to infinity, as long as the relative entropy is non-negative. If the relative entropy is 0, this probability goes to half, which is basically saying that you can't distinguish between, if I give you n samples, there's no way for you to tell me if it came from the distribution P or the distribution Q. But if this number is anything that's off 0, if it's any positive number, then this probability asymptotically goes to 1 as the number of samples you draw out become larger and larger, and this just tells you that if this number is anything of 0, there is always you can always distinguish between the two distributions. If I give you a large number of samples, you can tell me what distribution they actually come from. But the larger the number, the lesser the number of samples you actually need in order to make this distinction. Okay. This is again, all the last few minutes I spent only talking about information theory. There's no thermodynamics here, but surprisingly, it turns out that these objects, which look like really arcane information theoretic concepts, they show up very naturally, and we'll do that in tomorrow's lecture. They show up very naturally when you start writing down ideas like the second law of thermodynamics for DNA replication processes or for DNA proofreading processes and so on and so forth. And we'll do that tomorrow, but I just wanted to spend some time talking about the basic information theoretic message that's contained in these examples, and that, information theoretically, the objects like D tell you about distinguishability between two distributions, and objects like S tell you about how much information can be encoded in a pulse or in a series of signals without any reference to thermodynamics or energies or anything like that. Okay, yeah. Yeah. Oh, I'm sorry. I ended up, so when you define this, I used, as Juan said, I can either use a log 2 or I can use a log to the base e, and in writing 2, I use log to the base 2 because that's sort of what you do when you do information theory. Again, when you do this in thermodynamics, you can write this as e to the power of minus n, and it works out the same way. So it's just a factor that comes from that. Yeah. Okay. So now that I have all this set up, let me just go ahead and try to work out the amount of information transfer that happens when I have a process of this sort. I have a signal that I'm actually interested in. It gets modified by some number g or by some constants g, and it also gets modified by some random noise. This random noise is basically coming from these fluctuation dissipation kind of constraints, and I want to sort of think about how much information is actually transferred in such a process. And so for that, I can compute the measured information. So what I want to do is I want to compute the mutual information of y and x to figure out how the random noise ends up affecting my information transfer. Again, I'm doing this because this is a simple exercise to do once, and this will lead me into, or this will be a good segue for me to talk about how I can use non-equilibrium forces to modify or to increase this mutual information, because that's what I want. I want processes that convey the most information, and for that, first I want to work out analytically what the mutual information for this thing looks like. If you assume Gaussian noises, which is a reasonable thing to do in almost all cases, it turns out that you can actually work this out very, very easily. So the probability of y given x, if the noise is Gaussian, is a very simple thing to do. This is simply proportional to the exponential of y minus gx whole squared by twice the variance of the random noise term. And so using this probability, one can work out the mutual information, and this works out to half log 2 1 plus, and again I'm going to log 2 here, okay, and you can sort of see some salient features here. The mutual information can be increased if I modify g. If I make g very large, I can actually improve the efficiency of information transfer. I can also improve the efficiency of information transfer by reducing the fluctuations in the random noise term that shows up over here. And as we discussed in the first part of this talk, the fluctuations in the random noise term are almost entirely come from fluctuation dissipation, like concentrations. They don't depend on the essential chemical features. They sort of depend on things like the diffusion and so on and so forth. So perhaps we can actually modify this or reduce this by going out of equilibrium and making information transfer more efficient. Okay, so let me for the last point, I still have some time. So for the last point, I'll make, I'll again say that I've talked about bits, I've talked about information. The question really is, does biology care about bits at all, or is all this just an abstract theoretical exercise? What I'll try to convince you in tomorrow's lectures is that if you were to write down the second law of thermodynamics for very simple biophysical, or actually for large parts of biophysical processes, ideas like these information theoretic ideas show up naturally, and they point to ways in which one can actually control the amount of noise that shows up. It points to ways in which you can transfer information more efficiently. It also points to ways in some cases in which you can protect the information you're transferring by going far from equilibrium. So I'll do all that in the next class or in the next lecture, but I'll set up the problem in the last few minutes. So one of the problems I'll be talking about for the most part has to do with DNA replication. And this has been a problem that has almost been like an Ising model to think about information transfer in biophysical contexts. So let me just sort of draw or sketch out the problem, and tomorrow I'll talk about this in more detail. So let's say I have a DNA polymerase that's coming in, and it's trying to replicate a strand of DNA. And this is my very, very poor man's representation of a DNA polymerase doing something to a strand of DNA. So this DNA strand has many base pairs, and so these are, I have some base pairs on this DNA strand, and in order for accurate replication, in order for cells to convey their information to the next generation accurately, you need this replication process to be very accurate, right? So if I have a certain kind of a base pair or a certain kind of a bond in the unreplicated strand, I want to recreate the same kind of bonds or the same kind of patterns in the replicated strand. So I want to be able to do processes in which I have very little noise, and I basically almost have a deterministic process. That's what I want, but obviously thermodynamics doesn't allow that. So to be precise, if you look at the biochemical, so these are my representations of the base pairs that show up in the DNA. If the thermodynamically the states that are thermodynamically most favorable are states in which A is bound to T or G is bound to C. So A, T, G, C are the 4 base pairs that show up in a DNA. So states like this have the lowest possible energy, but you can always have errors. You can have states in which A is bound to A incorrectly, and so on and so forth. These are higher energy states than states like this. Okay. So what I can do is I can actually go ahead and I can try to work out a very simple formula for an error rate. Okay, so I call my error rate eta, and my error rate is going to be from Boltzmann statistics is going to be the exponential of beta delta E, where delta E is the energy difference between the right base pairing and the wrong base pairing. So this is the right base pairing, and this is the wrong base pairing, and I can write down an energy difference delta E between these two things. And if I know what this energy difference is, I know that the error rate that I get, I can I can come up with a very simple formula for the error rate that you will get as the system tries to form a new strand. It always wants to be in a state like this, but due to thermal fluctuations, every so often it goes to a state like this, which should be suppressed because this kills the fidelity of DNA replication. This adds noise, from just from Boltzmann statistics, you can work out and you can show that the error rate scales like the exponential of minus beta times delta E, where delta E is the difference of binding energies between this state and this state. Okay, so if you actually work out what this eta should be by measuring, this is a quantity that you can actually measure in experiments. You end up getting an answer that's roughly around 10 to the power of minus 2 to 10 to the power of minus 4. I might be on the higher end here, but it's something on this magnitude. So this tells you that 1 every 10,000 base pairs, purely from thermodynamic considerations, if you just think about the energies, 1 every 10,000 tries, you're going to get an error. And this is a hopeless process. So if we had such errors propagating throughout biology, we would all be mutants or dead by now, and that doesn't happen, obviously. So if you actually go and measure the error rates that are really seen in biophysical problems or in a DNA replication process, the actual error rate is roughly 10 to the power of -8 or lower. So it's roughly 2 orders of magnitude, or actually it's 4 orders of magnitude lower than what you get purely from equilibrium considerations. So in some sense, this error rate reflects our fluctuation dissipation bound for the noise. And that is on the order of 10 to the power of -4. What you actually see is what is seen in biology is much, much lower. It's 10 to the power of -8. And the question is, how does it happen? Hopfield and others in the 1970s considered this problem, and they figured out that by using non-equilibrium forces, you can actually modify these processes and reduce the error rates to these acceptable numbers. And actually, you can go way beyond this. You can sort of get a very general class of information processing ideas that emerge from this, from Hopfield's work. And we'll start tomorrow. We will take a look at how you can go from something like this to something like this, and how ideas like information theory and mutual entropy, mutual information and relative entropy show up again. Yeah, thanks. Any questions about anything?